In middle school, we were all taught that the expression a plus b whole thing squared is equivalent to the expression a squared plus 2ab plus b squared, which we can easily prove by expanding the terms a plus b times a plus b. As we grow older, we learned a more generalized form for expansions with the form a plus b power n, which, to the despair of many high schoolers around the world, is not a to the n plus b to the n, but rather this. This generalized form is what we know as the binomial theorem. Soon, you find yourself playing around with n equals 3, n equals 4, and maybe, if the question is feeling especially frivolous, n equals 200. Let's take a step back and look at this formula here. Don't you find it oddly beautiful? I mean, statistics appear when we expand something? What's up with that? Well, in this video, we shall be delving into the hidden relation between these two fields of study, and hopefully you'll get to see the beautiful connection behind it. But first, I think a recap of the binomial theorem wouldn't hurt. For the uninitiated, the binomial theorem goes like this. Let's say there is an expression a plus b to the power of n. If we wanted to expand this, what would we get? Well, the binomial theorem states that this expression is equivalent to this. Now, this might look complicated, but hear me out here. You take a and b here, and you raise it to the nth power. So here you would have a to the n plus b to the n. Thinking about it logically, these terms come from multiplying all the a terms in the expansion and all the b terms. For the middle, we follow a simple pattern. For a, we decrease the power by 1 each time, giving us a to the n minus 1, a to the n minus 2, a to the n minus 3, and so on, until we reach a to the power 0, or 1. For b, we increase the power by 1 each time, starting from 1, or b to the power 0. This gives us b to the power 0, b to the power 1, b to the power 2, etc. until we hit b to the power of n. These are all terms in the expansion. Easy, right? Well, we're missing one crucial detail, the coefficients. For a reason that we'll get into later, the coefficients of these expansions are the combinatoric term n choose r, where r is the position of the term minus 1. For example, the first term is n choose 0, the second term is n choose 1, third is n choose 2, and so on until we reach n choose n at the end. Now, we just combine these terms and voila! This is the binomial theorem. Do note that alternatively, many texts also write the coefficients as shown. They generally mean the same thing, just written differently. Now that we have a general idea of what the binomial theorem is, let's try it out with an example. Let's take the example of the power being 4. We'll do it the same as just now. Take a to the 4 and b to the 4 on both sides. Then, reduce the powers of a by 1 in each term, and increase the powers of b by 1 on each term. Then, to generate the coefficients, we substitute n equals 4 into NCR and the respective positions into R. We then get these numbers as the coefficients, which in our case simply resolve to 1, 4, 6, 4, and 1. Therefore, for the binomial theorem, we know that this is the expansion of a plus b to the 4th power. So, after all that, I think the glaring question, first and foremost, is this n choose algebraic? Like, what in the Hagoromo chalk even is this? And for those who haven't taken a module in stats yet, what even is n choose r? As mentioned earlier, we're going to answer both questions so that you can get a deeper understanding of what exactly this theorem means when it plainly states n choose r. And we will also establish a link between the two concepts. Without further ado, let's get into it. The field of combinatorics aims to answer a simple question. Given n objects, how many ways can we pick r of them? For example, let's say you have 3 balls, a blue ball, a red ball, and a yellow ball. The notion of combinatorics, simply put, is to ask, how many ways am I able to pick a certain number of balls from this set? Say we want to choose 2 balls. How many ways can we do this? Well, we can list out all the options that we have here. Blue-red, red-yellow, and yellow-blue. So, we have a total of 3 options here. Therefore, the value of 3 choose 2 is 3. Some of you may ask, wait, what about red-blue, yellow-red, and blue-yellow? Well, notice that the difference between these two groups is just the order of the balls. When we talk about combinations, we only care about what balls we choose, rather than in what order we choose them in. When we care about the order, we call them permutations, rather than combinations. Here's another example, with 4 balls, red, green, yellow, and blue. If we want to select 3, here are options for the number of permutations, in which order matters. In all, there are 24 permutations. Notice that between the rows here, the combinations of the balls are the same. It's just that the order is different. Therefore, looking at one of these rows, we can conclude that 4 choose 3 is simply 4. You might be asking, what if there are 200 objects and we want to select 100 of them? How does this magic calculator machine know what this value is? Surely they don't list out all the combinations. Well, with 90 octodecillion results, we can assure you that there is a better way of doing things. It involves a neat little formula that you can check out in this video. Back to the binomial theorem. Now that we have recapped the binomial theorem and explained what combinatorics is at a glance, let's take a look at why these two concepts, seemingly distant, are necessarily related. Let's take a look at the term x plus y to the third power for a second here. If we expand it, we will get this expression. Alright, but where does this take us? Well, the solution requires a shift in perspective. What if we expand it without grouping the terms that repeat, like so? Let's rearrange these terms to sort them in terms of the amount of x's and y's that they have. We notice that these terms will contribute to the x squared y term, and these will contribute to the xy squared term. And these two here will simply be x cubed and y cubed accordingly. Look closely at all of these. Notice how these terms here all have 3 digits. This is simply because we are multiplying 3 x's or y's at any point in time, leading to the terms of length 3. If we expand for power 4, the terms will likewise have 4 digits, and 5 digits for power 5. So, for this case of 3, let's generalize the terms as 3 slots. Let's color these slots red, blue, and yellow. When we're looking at the number of x squared y terms, for example, what we are really asking is that how many ways are there to have 2 x terms within these 3 slots? Well, if we were to list out the possible places we can fit 2 x terms within these 3 slots, we will have red blue, red yellow, and yellow blue. Does this sound familiar to you? Well, my friends, this is why n choose r appears in the binomial theorem. Whether we are choosing balls or choosing slots to fit x in, both are ultimately the same process. When we ask for coefficients, we are in effect asking how many ways are there to pick r slots from n slots to assign the x term, which basically is the fundamental question that n choose r attempts to solve. Thus, it makes perfect sense that n choose r must appear within this equation. And that, my friends, is the simple reason why statistics appears in the binomial theorem. Isn't it beautiful? We often draw a line in the sand between the practical realm of statistics and the abstract realm of pure mathematics. And yet here, at the very foundations, lie a deep and intrinsic connection. I think that just the mere fact that this connection even exists is just incredible, and I hope that you think so too. In the next video, we shall be explaining a curious connection between combinatorics and a certain familiar triangle. I'll see you in that one.